Welcome to this presentation on entanglements via slip springs with soft, coarse-grained models. This work explores how topological constraints in polymer systems can be effectively modeled with mesoscopic methods, focusing on the relevance of entanglements to material behavior near interfaces. This study addresses the challenge of representing polymer entanglements in simulations of polymer melts and liquids, especially near interfaces such as liquid-vapor boundaries. Entanglements strongly influence the mechanical and dynamical properties of polymer materials. However, atomistic models with explicit entanglements are computationally expensive, limiting the accessible length and timescales. To overcome this, the authors use a combination of the many-body dissipative particle dynamics (MDPD) method for soft coarse-grained interactions and introduce slip springs (SLSPs) to impose topological constraints that mimic entanglements without preventing chain crossings explicitly. This modeling approach allows the independent tuning of static and dynamic properties, enabling efficient simulations of polymers with realistic entanglement behavior in complex geometries, including near free interfaces. The question at the heart of this work is whether the SLSP model, integrated with MDPD, can faithfully reproduce entanglement effects and the associated polymer dynamics in such environments. The authors compare their SLSP model results to those obtained from the well-established Coarse-Grained KG polymer model, which features explicit entanglements due to strong excluded volume and bonding potentials. Through this comparison, they validate the SLSP approach's ability to capture key static and dynamic features of polymer entanglements. Their results show that the SLSP model can replicate features such as entanglement density profiles and breakup dynamics characteristic of real polymer systems. This suggests SLSPs in soft coarse-grained models offer a promising and computationally efficient route to study polymers under conditions where entanglement topology is critical. Figure 1 presents a schematic depiction of the SLSP model applied near a liquid-vapor interface. The model builds on many-body dissipative particle dynamics, or MDPD, which describes the non-bonded interactions between coarse-grained polymer beads. The model explicitly incorporates topological constraints through slip springs, represented as connectors from a highlighted blue polymer chain to adjacent black chains. Importantly, while in the liquid phase, the chains are topologically constrained via these slip springs, the vapor phase does not enforce such constraints, and instead simply reflects where the chain contours terminate. This treatment acknowledges that entanglements influence polymer dynamics primarily in the condensed phase. The SLSPs act as virtual springs that confer entanglement effects without strictly forbidding chain crossings, thus allowing computationally efficient simulations. The figure encapsulates the conceptual framework in which the polymer segments are connected by slip springs in the dense phase, capturing the network structure of an entangled polymer melt, while the interface allows relaxation of these constraints as chains exit into the vapor. This schematic underlines the key innovation of the model, embedding topological constraints in a coarse-grained, soft particle framework integrated with MDPD that realistically represents interfacial polymer behavior. Figure 2 demonstrates the critical importance of separating dynamic and static properties in the SLSP and MDPD framework to allow independent tuning during coarse graining. To model substrate effects, the authors implement a Lennard-Jones type wall represented by a potential parameterized with specified epsilon and sigma values, creating realistic particle wall interactions. An important difference is noted between MDPD and classical dissipative particle dynamics (DPD). MDPD better reproduces realistic packing near interfaces and compensates for the so-called missing neighbor effect, although this compensation is not strictly necessary. The figure includes density profiles for liquid-vapor systems with and without a compensating potential, illustrating that without this compensation, the interface location and shape shift undesirably. This impacts the interface stability and particle arrangement near walls, as highlighted by density changes near the wall-liquid interface for different entanglement levels controlled by the fugacity parameter Z. The authors validate their SLSP model by comparison to the well-established entangled Coarse-Grained model. The KG model uses strong Lennard-Jones repulsion combined with a Fenny potential limiting bond extensibility, effectively preventing chain crossings and thus generating explicit entanglements. Two refinements are applied to KG chains: an angle potential that slightly stiffens chains to encourage entanglements, and an extended cutoff with attractive interactions added to simulate a liquid-vapor interface. The authors carefully equilibrate the KG systems using a soft push-off protocol to achieve realistic densities. This combination sets up a baseline against which the SLSP model can be compared, especially regarding density and topological features near interfaces and substrates. Figure 3 compares the concentration profiles of slip springs in the SLSP model and kinks in the primitive path of the KG chains near a liquid-vapor interface. These profiles were obtained using the Z1+ algorithm, which identifies topological constraints in polymer melts. For clarity, the data are shifted along the horizontal axis and normalized to overlap with the density and chain end density profiles. Both approaches exhibit similar qualitative trends. The density of both kinks and slip springs is broadly constant in the bulk polymer, with a subtle decrease near the interface. This decrease arises because polymer chains adjacent to the interface have fewer neighboring chains on the vapor side with which to entangle. Correspondingly, there is an enrichment of chain ends close to the interface in both models, consistent with chain statistics at free surfaces. This agreement between the SLSP and KG models confirms that the static properties of polymer entanglements are well captured by the slip spring construction within the MDPD framework. Thus, the SLSP model reproduces key entanglement-related structural features observed in the detailed KG simulations, despite its coarser, more computationally tractable representation. Figure 4 depicts the temporal evolution of a polymer stalk connecting two plates as simulated with the KG model. The snapshots progress from the initial stalk formation to linear thinning and finally to an exponential decay, leading to breakup. The figure shows two types of images for each time point. On the left, the polymer particles are visible, whereas on the right, the particles are made transparent to highlight the entanglements in red. In this KG model, the entanglements correspond to kinks identified by the Z1+ algorithm. The images reveal how the polymer network adapts dynamically under confinement and wetting conditions, with the topology playing a decisive role in the thinning dynamics. This detailed visualization emphasizes the rich structural changes involved in the breakup processes of entangled polymer films under realistic conditions modeled here with the well-validated KG approach. Figure 5 shows the analogous sequence to Figure 4, but using the SLSP model framework. Over time, the stalk connecting two plates transforms from its initial state through linear thinning and eventually to exponential decay prior to breakup. As in the KG case, the left images display the polymer particles, while the right images render the particles as transparent to highlight entanglements shown in red. In this SLSP model, entanglements are visualized directly as slip spring bonds, which represent the topological constraints in the coarse-grained system. Remarkably, the dynamic evolution of the polymer configuration and entanglement network closely parallels that observed in the KG model, signifying that the SLSP model captures the essential topological dynamics during process conditions such as breakup under confinement and wetting. This visual correspondence supports the SLSP approach as an efficient mesoscale method to study polymer entanglement dynamics in complex geometries. Figure 6 quantitatively compares the neck size evolution of the capillary breakup of a polymer meniscus between two plates, as predicted by both the KG and SLSP models. The blue curve represents the KG results, while the red curve shows the SLSP predictions. Both models display hallmark breakup regimes known from theory and experiments, beginning with an initial linear decrease in neck radius, followed by a transition to an exponential thinning regime dominated by entanglement relaxation. The inset highlights the initial linear decay, whereas slightly faster thinning is observed in the KG simulations, likely due to subtle differences in surface tension relative to the implicit viscosity matching between the models. In the terminal regime, both models show exponential decay, with closely matched relaxation times, approximately 1.2 times 10 to the 4 tau-j for both SLSP and KG systems, indicating remarkable quantitative agreement. This alignment underscores that the MDPD approach, combined with the SLSP model, using comparable bulk parameters, effectively captures the capillary breakup rheology of entangled polymers. The SLSP model's excellent qualitative and quantitative reproduction of theoretical predictions positions it as a powerful tool for nanorheology and interpreting experiments involving complex polymer interfaces and breakup dynamics, enabling efficient mesoscale simulations that include topological constraints. In conclusion, this work demonstrates that the slip spring SLSP model integrated with many-body dissipative particle dynamics MDPD offers a powerful coarse-grained framework to simulate polymer entanglements efficiently, even in the presence of complex interfaces such as liquid-vapor boundaries. The authors validate the SLSP model by direct comparison to the well-established Kremer-Grest KG model, showing excellent agreement in both static entanglement distributions and dynamic processes like filament thinning and breakup. Key features such as the decrease of entanglement density near interfaces and the enrichment of chain ends are captured equally well by the SLSP model. Dynamic measurements, including the time evolution of neck radius during capillary breakup, align very closely between the two models in both linear and entanglement-controlled exponential thinning regimes. These findings highlight that the SLSP approach can reproduce essential topological constraints without explicitly forbidding chain crossing, thus enabling simulations of larger systems and longer timescales than atomistic methods. The ability to independently tune static and dynamic properties and to integrate realistic interfaces enhances the model's versatility. Overall, the SLSP and MDPD combination holds great promise for advancing multiscale modeling of polymer rheology, wetting, and nanorheological phenomena in situations where entanglement topology critically governs material behavior.